In this video, we will determine the strongest intermolecular force in a molecule. If you're not familiar with drawing Lewis structures or determining whether a molecule is polar or nonpolar, make sure to watch those videos before you tackle intermolecular forces. The first question when we're encountering a molecular formula that we will ask ourselves is the compound ionic? And if it is, the only intermolecular force, or the strongest intermolecular force it has is ionic. And you don't have to think about it any further than that. You don't have to do any of the subsequent steps, because if it's an ionic compound, it has ionic bonding. And note that ionic bonding only occurs in ionic compounds. So you cannot have ionic bonding if you have a covalent compound. There are a couple of ways you can recognize an ionic compound. It could be a metal bonded to a nonmetal, like sodium chloride, for example, or it could contain a polyatomic ion, for example, carbonate. So if you were to have polyatomic ions bonded to each other, or a metal bonded to a polyatomic ion, it's an ionic compound, and its intermolecular force is ionic bonding. Now, if we don't have an ionic compound, then the next question we ask ourselves is, does this molecule have a polar bond? And for that, we will calculate the difference in electronegativity for each bond present in the molecule, and then we'll proceed from there. So if we calculate the electronegativity differences and we find that it does not have a polar bond, then it must be a nonpolar molecule. In order to be polar, it has to have at least one polar bond. Now, if it's a nonpolar molecule, the only intermolecular force that it has is dispersion. And then you don't have to do anything past that. You don't have to determine the structure. You don't have to think about the dipoles or whether they cancel. Right off the bat, you know it's a nonpolar molecule. Now, if we find that it does have a polar bond, then things get a little bit more complicated, because just because we have a polar bond does not mean that the molecule overall is polar. And in that scenario, we need to draw the Lewis structure, determine the molecular shape of the molecule, draw the appropriate dipoles, and then determine whether they cancel. If the dipoles do cancel, then the molecule is nonpolar and its intermolecular force is dispersion. If the dipoles don't cancel, then it is a polar molecule, and then we have a couple of options. It could be dipole-dipole or hydrogen bonding. So only polar molecules that are covalent have dipole-dipole or potentially hydrogen bonding. However, hydrogen bonding only occurs in molecules that have an OH bond or an NH bond. So hydrogen must be present, and it must be directly bonded to oxygen or directly bonded to nitrogen. Be careful with that, because sometimes people take a look at a molecule, they see that it has a hydrogen, and they instantly think hydrogen bonding. But that hydrogen must be bonded to oxygen or nitrogen, because those are the only two atoms that are electronegative enough to do hydrogen bonding. Hydrogen bonding is effectively a stronger version of dipole-dipole bonding. Okay, now that we have that information, let's try a few examples and think our way through this process. So the first that we will take a look at is sodium bromide. And you may recognize this as an ionic compound because we have a metal and a nonmetal. But if you weren't sure, what you could do is calculate the electronegativity differences between those two and see whether there is a polar bond or where that bond falls in the process. Looking at the electronegativity chart, sodium is 0.93. Bromide is 2.96. And what we're going to do is subtract those two values to determine the electronegativity difference, and it is 2.03. That is a really, really huge number, and that is definitely an ionic bond. Now, looking at that chart, we determine that if a compound is ionic, immediately we know it is a polar molecule and its intermolecular force is ionic bonding. And we don't have to think about it any past that. As soon as we know it's ionic, it has ionic bonding, and we can leave it at that. Let's try the next one. And I'll copy that over to the next page. The first question I will ask myself is, does this molecule have a polar bond? And I see that this is going to contain 2 hydrogen-sulfur bonds. So I'm going to calculate the electronegativity differences between these 2 elements. And looking at the chart, hydrogen is 2.2 and sulfur is 2.58. Then I'm going to subtract those 2, and we're getting a difference of 0.38. That would fall into the nonpolar covalent bond category. And if you're not sure about where these numbers are coming from, you can go back and watch the video on determining whether a molecule is polar or nonpolar. We had the chart that had the cutoffs for these numbers in that video. We have a nonpolar covalent bond, which means that the answer to this question of does this molecule have a polar bond is no. And if it doesn't have a polar bond, immediately it is a nonpolar molecule, and the only intermolecular force it has is dispersion. So nonpolar covalent bond means this is a nonpolar molecule, and its intermolecular force is dispersion. And that's it. We do not have to think about this any further than that. Let's try another one. Okay, so just like with the previous problem, the first question I will ask myself is there a polar bond? And I see that there is 1 carbon and 4 chlorines, which means we're definitely going to have a carbon-chlorine bond. So I'm going to look at their electronegativities. We see that carbon is 2.55 and chlorine is 3.16. I'm going to calculate the electronegativity difference between them. And that falls into the polar covalent category. So we definitely have a polar bond. Now, looking back at this chart, that gives us an answer of yes to the does the molecule have a polar bond question, which means now we have to think about whether the whole molecule is polar. We have a polar bond, but that doesn't necessarily mean that the molecule is polar. So we'll check that out. We're going to draw the Lewis structure, determine the molecular shape, and then draw the appropriate dipoles. So this takes us back to our drawing Lewis structures video. And the first thing I'm going to do is determine how many valence electrons each atom has. Looking at the periodic table, so these group numbers are not labeled here, but this would be group 1A, 2A, 3A, 4A, 5A, 6A. Ooh, I'm running out of space here. Okay. Carbon is in group 4, which means it has 4 valence electrons, and chlorine is in group 7, which means it has 7 valence electrons. So carbon is contributing 4 valence electrons, chlorine is contributing 7 valence electrons. Looking at the molecular formula, there are 4 chlorines in the structure, which means we have to account for that when we're putting the molecule together. So I'm going to multiply that by 4 and then add in the electrons that come from carbon. And then I'm going to add all of those together for the total electrons in the molecule. Now, carbon has 4 valence electrons, which means it needs 4 more in order to complete its octet. So carbon needs to make 4 bonds. Chlorine has 7 valence electrons, which means it needs only 1 more to complete its octet. So chlorine wants to make 1 bond. That means I'm going to put carbon in the center of the molecule and surround it with chlorines. We're going to draw single bonds between all of them, which use up 8 valence electrons, and then we'll distribute the remaining electrons around the outer atoms and then check that everybody has an octet. So that's 8 electrons so far. This would be 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So now I've distributed all of my electrons. I see that carbon has access to 8 valence electrons, so it has its octet fulfilled and it is good to go. And this chlorine has access to 8 valence electrons, so its octet is fulfilled and it is good to go. And notice that all of the chlorines are exactly the same, so every atom in this molecule is happy with its situation right now. The next thing we have to do, so that was the Lewis structure. The next thing we have to do is determine the shape of the molecule. And for that, notice that around the central atom, there are 4 electron groups, which means that the electronic shape is tetrahedral. And the central atom doesn't have any lone pairs of electrons, so the molecular shape is also tetrahedral. I will draw the molecule in the tetrahedral shape. And then I will figure out where the dipoles are heading. So keep in mind that the more electronegative atom is going to pull the electrons in the bond toward itself. And if we look back at our chart, chlorine has a higher electronegativity than carbon, which means that chlorine is pulling the electrons in each of these bonds toward itself. Now notice that this molecule is completely symmetric. These dipoles are heading in equal and opposite directions, which means that these dipoles cancel. And if we look back at our chart, if the dipoles cancel, then this is a nonpolar molecule, and the only intermolecular force is dispersion. So you can see how things get considerably more complex once you have a polar bond and you have to figure out what's going on with the rest of the molecule. So polar bond does not necessarily mean that the molecule overall is polar. Okay, let's try another one. Same type of thing we did before. The first question I will ask myself is there a polar bond? So I'm going to calculate the electronegativity differences between these two atoms. I forgot the value for oxygen. Oxygen is 3.44. So I'm going to subtract these two values. And that is a polar covalent bond. Okay, which means things will be a little bit more complex. Because if you recall, we determined this compound is definitely not ionic, it's all nonmetals. We see that we do have a polar bond. So now we have to go through that entire process. We need the Lewis structure, the molecular shape, and the dipoles. Okay. Hydrogen, if we were to look back at the periodic table, we see that it's in group 1A, which means it has 1 valence electron. Oxygen is in group 6A, which means it has 6 valence electrons. Now keep in mind that there are 2 hydrogens in the structure, so I have to multiply that by 2 to account for that. And then I'm going to add these up to determine the total valence electrons in the entire molecule. Now, because oxygen has 6 valence electrons, it needs to make 2 bonds to complete its octet. Recall that hydrogen is one of the exceptions to the octet rule. It only wants 2 valence electrons, so it only needs to make 1 bond. Because oxygen needs to make more bonds, I'm going to put it in the center of the molecule, and then I'll connect everything else. So I'm going to start by making a single bond. As soon as I do that, the hydrogens are happy. They already have 1 bond each. Oxygen has 2 bonds. So I'm going to distribute the remaining electrons to the oxygen because it doesn't have an octet right now. So we used up 4 valence electrons, and I'm going to give the remaining 4 to oxygen. If we look at that, we see that hydrogen has access to 2 electrons, so it is happy. It has fulfilled its duet. Oxygen has access to 8 valence electrons. It is happy with that situation. Now we need to determine the molecular shape. So the central atom has 4 electron groups around it, which means that the electronic geometry is tetrahedral. However, it has 2 lone pairs of electrons around it, which means its molecular geometry is bent. And if you're not sure, you can check out the molecular shapes video to make sure that that makes sense. So the molecular shape is bent, which means that the structure is actually going to look like this. Okay. Now, looking at the electronegativities, oxygen is much more electronegative than hydrogen. So oxygen is going to be pulling the electron density in each of these bonds toward itself. So now we have 2 dipoles that are pointing up. And notice that up top, we only have lone pairs of electrons. They don't have dipoles. So we have both dipoles pointing up, which means overall there is a dipole pointing up. So these dipoles definitely do not cancel. This molecule is not completely symmetric because we have 2 bonds down here, but then no bonds up here. Those are just lone pairs of electrons. And if the dipoles do not cancel, then the molecule is polar. And now we have 2 options. This could be dipole-dipole or hydrogen bonding. Notice that hydrogen bonding only occurs when we have OH bonds or NH bonds. And here we definitely have OH bonds. So the molecule is polar. Because the dipoles do not cancel. And the intermolecular force is hydrogen bonding. Let's try one more example. Okay, so here we need to determine whether or not we have a polar bond. And here might actually be a little bit tricky if you're not familiar with this molecule to just look at it and know what kind of bonds you have. So you may actually want to start by drawing the Lewis structure. We know that hydrogen has 1 valence electron, carbon has 4 valence electrons, and oxygen has 6 valence electrons. There are 2 hydrogens in the molecule, so I'm going to multiply the electrons by 2 to account for that. And then I'll add everything up to determine the total valence electrons in the entire structure. Okay, now looking at that, hydrogen only wants 1 bond, carbon wants 4 bonds, and oxygen wants 2. And since carbon wants the most bonds, I'm going to put carbon in the middle, and then I'm going to connect everything else to carbon. I'm going to start by drawing single bonds between all of them, and then I can distribute the remaining electrons around the outer atoms and check if everybody has an octet. This used up 6 valence electrons, so this would be 8, 10, and 12. Now notice I distributed all of the electrons. Hydrogens are happy with the 2 electrons they have access to. Oxygen is happy with the 8 valence electrons it has around it, but carbon right now is missing 2 valence electrons. It only has 6 and it wants 8 to complete its octet. However, we've distributed all of the electrons we have access to, which means the only way that we can have an octet on all of the atoms is if we use 2 of these lone pairs to make a double bond. And once we make a double bond, every atom in the molecule has an octet. Now, oxygen has access to 8 valence electrons, carbon has access to 8 valence electrons, and each hydrogen has access to 2. So that would be the Lewis structure of the molecule. Now that we have that information, we see that there are 2 different types of bonds here. There is a CO bond, and there is a CH bond. So we need to determine whether each of these is polar or nonpolar. carbon has an electronegativity of 2.55, hydrogen of 2.2, and if we subtract those two values, we have 0.35, which means this is a nonpolar bond. Okay, so we don't have to worry about that bond in particular, but we do need to examine the carbon-oxygen bond and see if that is polar. I forget the value for oxygen, that was 3.44. And if we subtract those two, that gives us a value of 0.89, which is definitely a polar bond. Okay. As soon as we have a polar bond, we do need to think about this further. So we are here now. And since we have a polar bond, we need to draw the Lewis structure, which we fortunately already did. We need to determine the molecular shape, draw the dipoles, and see if those dipoles cancel. Okay. The central atom has three electron groups around it, which means both the electronic shape and the molecular shape is trigonal planar. The shapes are the same here because there is no lone pair of electrons around the central atom. So the molecule shape is trigonal planar. Which it looks like this. And now we need to figure out where these dipoles are going. Keep in mind that the carbon-hydrogen bonds are nonpolar, so these are not going to have a dipole. The carbon-oxygen bond is polar, and oxygen is the more electronegative atom since it has a higher electronegativity value. So there is a dipole pointing in the direction of oxygen, and there is nothing to counteract it because the carbon-hydrogen bonds are nonpolar. They do not have a dipole that can counteract the carbon-oxygen dipole. And here, if there's only one dipole, the dipoles definitely do not cancel, which means this is a polar molecule. I am running out of space here. Okay. The next thing we're going to think about, so we do not have dipoles canceling, definitely polar molecule, which means there are two possibilities. It could be dipole-dipole, or it could be hydrogen bonding. But keep in mind that hydrogen bonding only occurs when you have an OH bond or an NH bond. And be careful here because we do have some hydrogens, but that hydrogen is connected to carbon, not to oxygen. So here the intermolecular force will be dipole-dipole. Okay. In summary, definitely ask yourself these questions in the order that they are listed on this flowchart, because you can cut down on a lot of work by recognizing when a compound is ionic or recognizing when the compound is nonpolar. If you don't have a polar bond, then you can skip a lot of this work and immediately identify that it's going to be dispersion. It's only when there is a polar bond in the molecule that you need to consider the shape of the molecule and go through the entire process.